Hello, everyone. So I'm Coleman Kendrick, and I'll be talking about using Numba for GPU acceleration of Neutron Beamline digital twins. So this is using MCViNE, which is a software package to do this. So first off, I wanted to kind of just give an overview of what Numba is. So Numba is an open source just-in-time compiler for Python using LLVM as the backend. And so the main kind of draw to Numba is the ability to parallelize code using only a decorator. So the idea is you can add a decorator to a Python function, and it will translate the Python code into machine code, similar to kind of how you would write it in C. So the advantage is to get the performance of C using Python. So this supports a large subset of NumPy functions. So if you're using existing NumPy functions or data structures, this will work with Numba. It also has support for kind of the universal functions of NumPy, which can be beneficial for some applications. So Numba also has a wide variety of platforms. So it can support AMD 64 as well as ARM, PowerPC, and things like that. And so it has GPU support with CUDA, and that's primarily what I'll be talking about today. I encourage anyone who is interested in Numba to go look at their homepage here. They have a lot of good tutorials and kind of documentation about the package and how to use it. So kind of going out into kind of the motivation for this project. So Oak Ridge is home to the spatial neutron source, which is called SNS. And so from the name, this is generating neutrons through spallation. So this is particles are accelerated in a linear accelerator, and they're being essentially pulsed into a liquid mercury target, which generates the neutrons. So on the right here, you can see kind of the collection of instruments that we have on site. So these neutrons are being sent down a beamline, and all these instruments are collected around that beamline, and they're used to simulate, kind of look at experiment for a lot of different physics and chemistry applications. And so this large suite of instruments, as you can imagine, collects a lot of data, and we need a lot of software to analyze this data as well. So additionally, Oak Ridge has been planning the second target station for quite some time now. And so this is a planned facility to basically double the power of the accelerator. So double the output, put in an additional beamline, and on that beamline, we have a new facility with support for up to 22 instruments, 8 of which are planned initially. And so we have these facilities for experimental neutrons experiments, and we want to be able to actually simulate these as well, because that will kind of allow us to get a better understanding of what's going on in the experiment, as well as kind of capturing different physics. And so simulation of this is very powerful as well, and very important. So the second target station is can be seen by this white building there, and that's kind of the planned area where it's being built. So simulating is very powerful, and that's kind of what MCViNE is for. So MCViNE stands for Monte Carlo Virtual Neutron Experiment. So this is a neutron ray tracing package. So on the right here, on the top right, you can see the experiment. So this is experimental data result from the ARCS instrument. And on the bottom is the same simulation, or same experiment done with MCViNE with simulation. And so we're able to actually simulate the same kind of experimental data, but we can do a lot more kind of analysis on this as well. So we can kind of turn things on and off, and we have a lot more control over simulation than we do with the experiment. And so this is very beneficial to be able to do this. And so in addition, since we're building the second target station, we have all these instruments that we're planning on building. So it's very important to be able to use software like this to actually verify instrument design before spending kind of resources to actually implement and build these machines. So kind of currently where we're at, though, is MCViNE's very slow for tens of billions of neutrons, especially adding kind of complicated scattering physics. This is a major bottleneck, especially when trying to validate these instrument designs. We want kind of quick turnaround, and that's not the case currently. So that kind of leads us into what we're doing now, which is we want to provide GPU acceleration of this software. So some initial challenges, MCViNE is originally written in C++, or C and C++, with some bindings to Python for user interaction. So that's how users interact primarily with MCViNE, is solely through Python. However, it's very hard for scientists to add new components. Since everything's written in C, C++, a lot of the scientists at our facilities don't know C++, and so it's a very large barrier to implement new things. In addition, as I mentioned earlier, there's slow performance for these large simulations. It has support for MPI, but there's issues with kind of scaling up. Doesn't scale well, kind of breaks down. And the code is integrated with a lot of kind of similar packages like Mixtas. So there's kind of a large code base that's kind of complex, and simply porting that to CUDA is kind of a large undertaking. And so in addition to wanting to improve performance, we also want to target maintainability from the user point of view. And so this is kind of where Python and Numba comes in. We want to be able to kind of implement this in a way that will allow scientists to implement their own components and kind of scattering kernels themselves. So this is where this package comes in. This is kind of a new package that we're making called MCViNE.acc, which stands for the accelerated version of MCViNE. This is a new repo from scratch, written in pure Python using Numba. So we have CI pipelines, both for CPU and GPU as well, since we want to verify the results between them. And while we're doing this, we want to modernize the code base. So we're sticking with an object-oriented design approach. So part of the challenges for this is that we want to be backwards compatible with the original version of MCViNE. So we don't want to break any existing scripts or anything that the users are currently using. So we want to be able to support kind of what's already existing as well. And since we're implementing all these components back on the GPU, we want to be able to support kind of a mixture of CPU and GPU components, at least initially, since we won't be able to implement everything on the GPU kind of at the beginning. So we want to be able to provide the mixture of this with kind of no overhead to the user. So additionally, since we're implementing kind of new components on the GPU, we want to make sure that we don't break anything, so we want to validate each kind of implementation. So we have rigorous testing for each component, as well as instruments that we implement to make sure that the GPU version is performing the same kind of results as the CPU as well. So kind of an overview of how MCViNE simulations work. Basically, users create a script that defines an instrument. So an instrument here, kind of this example picture here shows you have a source, a guide, kind of a detector, and a sample as well. So this kind of combines a simple instrument. And on the right here, you can see an example of the proposed Verdi instrument going to the second target station. This shows that the instruments can be quite large with many different components combined, so they can get pretty complicated pretty quick. So sample components are kind of a special type of component. So that's kind of where a lot of the physics is actually being done and modeled. So they have a sample container, which is kind of defined using a constructive solid geometry. It's where you look at the actual material, the sample material, and they're modeling that geometry. That's being used for ray tracing. And we also have kind of scattering materials. So we define different input kind of chemical models and kind of scattering physics for that as well. So those are also user input to the simulation. So to implement this in Python, we wanted to have kind of an abstract base class for each component. And so this is an example of the simplest component that we have, which is called an arm. This literally just models a physical arm in the instrument, and it doesn't do anything to the neutrons. So you can see at the bottom here, there's this propagate method, which takes in an input neutron. And this input neutron is basically an array containing position, velocity, probability, and things like that. And so each component is expected to define this propagate method, because that's what the component, that defines the action of the component. So kind of how the neutrons are being processed by that component. And so you'll notice this propagate method has a kind of a decorator here called CUDA.git. And so this is the Numba syntax for defining a CUDA kernel. And we have this device equals true, which indicates that it should be compiled as a device function called from a kernel later on. And so this is the way of kind of implementing a component and then implementing the kind of the main loop or the body of that component on the GPU. So kind of backing up to look at kind of the overall structure of the instrument. So this is kind of an example of an input script that the user would provide. So this is kind of an example script of a source, a guide, and a monitor. And so this is kind of, you can look at it as basically a linked list of instrument components. And so we append each component at a certain position and orientation into the instrument, and a transformation matrix gets applied to translate neutrons from one coordinate system to another between components. And so this is kind of exactly what the user would provide MCViNE, and this would simulate. So if we're doing that on the CPU, that would be all we would need. But since we're wanting to put this script on the GPU, we need to do a lot more work, I guess, in order to be able to do that. And so we have to take that input script. We want it to be backwards compatible, so we have to take that exactly as it is, and we want to basically put that on the GPU. However, we have some challenges because these scripts can be kind of any collection or ordering of these components, and so we can't hard code a kernel to kind of model different instruments. We could, but that wouldn't be sustainable, I guess. So we kind of want to do this dynamically. So we want to take in the script and basically generate a new CUDA kernel for that instrument at runtime. And so that's kind of what we're doing here. So on the right is an example of that previous script is taken in. We basically parse it, and we're generating a new Python script which has a CUDA kernel here. And this script gets then imported and then run at runtime. And so this is where the just-in-time compilation comes in with Numba. And so this is kind of the device kernel for that script. And so this run script.run is the current CPU API. So this is how users would actually run the script. So we want to basically implement this as well. So the MCViNE.acc version has the same kind of interface. So as far as the user is concerned, they call this same exact function, and all this is being done behind the scenes for them. But now it's running on the GPU instead of the CPU. So this is a kind of a zoomed-in version of just the CUDA kernel for the simple instrument with a source guide and monitor. So as you can see, the top here is decorated with this CUDA.git. This is the decorator syntax for defining a global kernel, essentially. So we have different arguments taking in kind of the number of neutrons and the number of neutrons per thread. And if you're familiar with CUDA, this should look pretty similar. Numba has a lot of kind of the thread ID and block IDs that are used in CUDA. And so this is getting a one-dimensional grid and splitting the total neutrons over the number of GPU threads. So this is defining kind of how much work each GPU thread is going to be doing. So some GPU threads can be doing more than one neutron, for instance. So that's why we have this loop here. But inside this main body, we have these different propagate methods. And so if you remember from earlier, each component has a propagate method that it defines, which defines the action of the component. And so here we're actually calling propagate 0 refers to the first component of the instrument, propagate 1 is the second component, and so on. So we're basically calling these one after the other, applying the transformation matrix in between. And so this is how we're actually implementing. We have this kind of generated script that's calling each GPU kernel in sequence, and this is actually propagating the neutrons through the instrument on the GPU. So additionally, to support the sample kind of components, we have to do geometry and ray tracing of the sample environment. And so for that, we're using constructive solid geometry. So this is kind of a way to define complex shapes using simple primitives. So you can take simple shapes like a block, sphere, cylinder, and provide different operations like union and intersection and things like that to build up a complex shape. And so on the right here is an example of an annular sample can that is constructed using constructive solid geometry. And this is an example XML file used to specify that. And so we're parsing that XML file, and basically we have CUDA kernels for the primitives themselves. So we have a CUDA kernel that does the intersection with just a sphere or just a cylinder, as well as different operations such as the union and intersection. So we parse this input XML file, and we use the same process as before to basically go through and generate a kernel that calls all these together. So at the end, we're left with one kernel that does the intersection of this full complex shape at the bottom here. So we're using XML to kind of define these geometries. In addition, we're also using them to define scattering physics. So we have different scattering kernels defined. So we have isotropic, simple power diffraction, kind of simple scattering physics models. MCViNE has a lot more than these, but these are kind of currently what we have implemented. And so we're taking these user input XML files, which we're kind of stuck with because that's kind of how the code was originally written. So we're stuck with parsing XML, but we're applying the visitor and factory patterns to these when we're parsing them to generate CUDA kernels at runtime for these. And so these kernels, these scatterer kernels, for instance, could be a collection of more than one. And so that's what we call a composite scatterer. So that's if we want to chain multiple different kind of scattering models together, we can do that using this kind of factory method visitor pattern to generate a kernel that does all of these at once. And then that way, when the component actually calls the propagate method, that's all linked in just kind of at runtime. So we've created this GPU version of the package, but we want to be able to validate the results against the CPU version. Since we're going to be using this to validate instrument designs, we want to make sure that we didn't implement a bug or anything like that. So we want to be able to prove that we're able to reproduce previous results with MCViNE. So MCViNE was previously used to show that multiple scattering is needed to capture some experimental data. And so looking at uranium nitride on the ARCS instrument, on the left here, we see these kind of lines across, constant lines across Q with different bands and energy. And so this kind of constant lines was an experimental data feature. And the initial simulation of MCViNE showed that we did not get these kind of constant lines. They kind of dropped off towards the Q as the energy increased. And so this was kind of puzzling to us. And so we found out that this was because MCViNE was using single scattering only. And so to capture this, we needed multiple scattering to capture this kind of effect. And so in enabling multiple scattering, we were able to capture the same exact kind of experimental data. And so that was originally done on the CPU back in 2014, I believe. So now we're reproducing that results on the GPU, and that's what's plotted here on the left is the GPU results. And on the bottom right is the comparison between the CPU and GPU for each energy band. And so the CPU is the solid line, and the kind of the circle, open circles are the GPU results. So this shows that the GPU version provides the same kind of result as the CPU version. So we validated the kind of the results, but now we want to look at performance. That's kind of the entire reason of this project is we want to speed up things. So we want to see how that actually happened. So as we found, I guess kind of speed up depends largely on the instrument complexity, which I guess is not entirely surprising. So for instance, the source guide monitor instrument that I showed earlier, we were able to achieve a speed up of about 1700, which was good. But once we started adding more physics to this, the speed up kind of decreased pretty drastically. So the homogeneous single scatter isotropic sphere is kind of a simple instrument with a sample component. So it's kind of involving the ray tracing and all that. So that's the simplest example of that. And for that, we were able to achieve about 133 times. And so on the right here is a plot of that. So the blue curve, we have the single core of CPU. The green is a 16-core version, and the orange is the GPU, using a simple consumer-grade graphics card for that. So we're able to achieve decent performance for that, but when we go to the uranium nitride example, the single scattering adds more physics to that, and so our performance drops to about a 33 times speed up over the CPU, and then to capture everything that we need to do the multiple scattering, and so that's what we're left with at the end of the day is about a 10 times factor for this particular simulation. And so 10 times is not, we were originally expecting more, but this is still pretty beneficial because these simulation times take on the order of days to weeks. So now we're able to reduce that from days to just hours. And so part of this reason I think for the performance drop is that these components are very complex, use a lot of registers on the GPU, and that kind of limits how well it'll perform. Additionally, a lot of the more complicated physics modeling includes a lot of complicated geometry, and that includes conditional statements. GPUs do not like conditional statements at all, so this also limits the performance that we get. So we can see kind of we're starting off with good performance for really basic models and then kind of dropping, but still beneficial. So some kind of Numba experiences using Python and CUDA from Numba has allowed us to basically generate kernel code at runtime. So this allows us to basically dynamically generate these kernels and compile them at runtime. Trying to implement this in sticking with C++, for instance, and implementing this would have been much harder. It would have required substantially more developer effort. And so Python was a good choice for this. Numba also seems to be growing and improving, so Numba is constantly being updated. It's very active in the community as well. They just recently added official CUDA Python bindings, which is good. So Numba is constantly changing and adding more features. And overall, Numba is easy to get something running on the GPU with minimal kind of code changes needed. But this, of course, depends on the application, kind of what the data structures look like and that kind of thing. So some of the downsides, not every Python feature is fully supported in Numba. So for instance, classes, I believe they're experimental or work in progress at the moment, but exception handling and things like that is not fully supported. And so for this particular application, this was nothing majorly prohibitive to what we were trying to do, but it's worth noting that there's potentially some downsides or issues that might arise depending on the application. So in summary, we were able to basically create a new package for a GPU version of MCViNE. So this is easy to extend in Python. So the end result is that our scientists can actually write their own kernels in Python and be able to achieve the performance benefits of that. And so we're able to use Python with Numba to generate kernels dynamically. And we have kind of core infrastructure for a lot of the main components of MCViNE. So this is guides, samples, sources, monitors, things like that. We've implemented full ray tracing of generic shapes on the GPU, and we've implemented the Verity instrument planned for STS. And we've done single scattering and multiple scattering as well. So for future, we're looking at continually trying to profile and analyze performance now that we've kind of verified that things are working. We're looking to add more support for other STS instruments. So these are the proposed instruments that we're trying to validate the designs for. We need to finish implementing those so we can actually start using this to look at the instrument designs. We're looking at extending this further into looking at detector systems, which is a capability that's not originally supported in MCViNE, I think. We're also looking at adding multi-GPU and multi-node capabilities. So we're looking at scaling this up. Now that we have the single node working, we're looking at expanding that into kind of large clusters as well. And finally, we're looking at deploying this back to our MCViNE package on Conda. So thank you.
So other questions?
You spoke a lot of CUDA, obviously, but what about HIP and AMD?
Yeah, so I think Numba kind of, I forgot exactly when, probably about 5 or 10 years ago, they dropped support for HIP. So Numba, unfortunately, does not, at this moment, support AMD anymore. I'm not sure if this is something they're planning on adding back or not, but that's certainly something to consider. This is currently works for CUDA only at the moment.
Okay, thanks.
Hey there. Yeah, Numba, love it, great, use it for Python. For GPU stuff, my group has found that abstracting code into PyTorch makes it very flexible to be able to run on whatever AMD or TPU or GPU resources. I wonder, are there any like benchmarks that show like CUDA.jit versus maybe using one of those machine learning type frameworks? Like you don't have to use those frameworks for machine learning, right? You can use those just for GPU digital signal processing or whatever. And if there is, can I submit a PR to like, submit my own benchmark to that?
Yeah, I guess I'm not sure if there's any benchmarks be worth looking into for sure. I know there's also alternatives to Numba in addition to like PyTorch. There's like CuPy and things like that. So it'd be good to kind of do a comparison, a more detailed analysis of which package or which kind of approach gives the best performance as well as kind of flexibility for different platforms.
So full disclosure, I actually manage the Numba team. But I'm very excited about this talk. Also, as a former particle physicist, I'm really excited about this talk. I'm curious what's on your, and to actually answer a couple of previous things. Yeah, AMD support was dropped a few years ago. We found no one seemed to use it, and it was a little hard to work with their tool chain. So it could come back, but we haven't had a lot of demand for it. And I'm not aware of comparisons with PyTorch, although PyTorch really excels when you have sort of array-centric operations. And if you find yourself doing a lot of control flow logic, that tends to be where Numba works a little bit better. But the question I had for you is, what's on your wish list of things that didn't work on the GPU you wish did?
Yeah, I guess I ran into some issues with kind of like operator overloading for, like in CUDA, we can overload certain operators for like a packed, like a vector of 4 or something.
You wanted to be able to do operator overloading on certain sort of struct data type kind of things.
Yeah,
Okay.
so kind of looking at packed, we do a lot of like 3-dimensional vector, like
Right,
3-dimensional array kind of operations, and so we're implementing we have kind of a helper library that just does like vector additions or multiplications, and so having these operator overloads for that would have been, I think, very helpful.
Cool.
I think there's some ways to get it to work with Numba, but it's kind of not ideal at the moment.
Yep. One random other question. I noticed you're using consumer cards. Did you struggle with issues of whether you were getting 32 or 64-bit float operations, and how awkward was that?
Yeah, so I guess for this, that is something that we looked into. We're forcing, back on the source code, we have this, we're forcing the signature to be a Numba float, I guess. We have this defined to be either float 32 or 64. So we're forcing it to be float 64 just to make sure that everything's being looked at. So we're still using signatures, I guess, to force this, since Numba can kind of do that for you, but we want to force it.
So you wanted 64-bit on all of this?
Yes.
Okay,
Yeah.
cool.
Yeah, we have the ability to go to 32-bit though for, if you need faster simulation, but for a lot of these designs, we want to stick with float 64.
Cool. All right, thank you.
Yeah, thanks.
So is this 100% open source out on GitHub?
Yes.
All right,
Yes.
so coming from the National Lab framework, getting stuff out, it's different from lab to lab and division to division. How difficult was it for y'all to get this cleared and out in the open?
Yeah, I guess not difficult at all. I guess the original version of MCViNE was all open source and kind of brought in externally to Oak Ridge. And so all of our contributions have been kind of, that's helped, I think, having the existing code be open source. So we're able to kind of create this, it's kind of an addition to the existing code. And so basically, we had no issues trying to get this just released publicly.
Very lucky.
Yeah, yeah, definitely not always the case.
Are there any questions in the Slack?
No, I haven't seen any.
Okay. Well, I guess we still have a few minutes. So is this deployed to your hardware at the moment? Or?
Yeah, so that's a work in progress at the moment. We have kind of a workflow engine locally that has a lot of these packages deployed to them. And so that's part of this project, is to integrate these changes into that. So we have MCViNE kind of deployed, and we're using that for a lot of these instrument kind of post-processing workflows. And so we have a toggle in there that says use GPU or not. And so we're currently working on deploying that into the software. And so whether or not that Boolean will be toggled, that will basically use the GPU version or not. So
But testing must be difficult in that case, right? Because
yeah,
you have to test it live. So.
Yeah, so a lot of our code that we're implementing, we're having a lot of CI tests to verify that the GPU result matches the CPU results. So we're verifying both all the individual components as well as different instruments as well. But yeah, there's certainly always more validation to be done.
More questions?
Just since you mentioned the consumer card as the comparison, so are you thinking of upgrading that, or is there any reasons to stick with that?
Yes, yeah. So we're working on pulling this into an actual, like, real scientific card. So we've been running this on the A100 so far on an ARM-based system, and so we're looking at trying to optimize it for that. So that's kind of that's where we're going, I guess. These were just kind of initial benchmarks.
Yeah, because I guess you could get a lot more speed up.
Yeah, yeah, definitely. Yeah,
Yes.
it's a little.
So I haven't used Numba in a while, but can you replace that type, in the decorator with a type hint? Will it be able to extract it out of the type hint?
That's a good question. I'm not sure about that. Yeah, that might be more of an.
Okay, let's thank the speaker one more time.